in the School of Electronics Engineering, VIT University, Chennai campus. So today's topic is emulation of Internet of Things using Contiki. These are the agenda, that is we will have two categories. One is on Internet of Things, IoT. The second one is 5G. Under IoT, we will be focusing on semantic architecture, architectural layers, protocol stack for IoT, Contiki emulations, that is setup protocols RPL, 6LoWPAN, QoP. Under the category of 5G, we are going to focus on various elements, proposed 5G semantic architecture, IPv6 protocol compatibility, simulations through NS3. The research directions are 5G wireless networks with IPv6, wireless body area networks based IoT healthcare, intelligent transportation system, wireless sensor networks with localization and tracking, smart metering with IoT, smart precision controlled agriculture, industrial IoT, Industry 4.0. Setup tools used for IoT and 5G. We have under open source category, Contiki with Kuja, NS3, Omnet++. These things comes under open source. Under proprietary, we have a CallNet, MATLAB 2014A, OpNet, NetSim. Whereas we have emulation platforms like Raspberry Pi, Arduino for small and medium scale, ARM, Intel for large scale applications. Now we will focus on Internet of Things. Internet connected objects like RFID, sensors, activators, instruments and smart appliances. Context aware communication and computing mainly works with IPv6 rather IPv4, powered mainly by sensor nodes which are low cost, small size and power efficient, which this guarantees the real-time performance. IoT is a real-time transformational force that helps business and industries to show better performance and deliver better results through improved process efficiency, asset utilization and productivity. The growth and convergence of data, process and things on the internet creates more opportunities for people and industries. So we have various sectors starting from home, that is smart home. We have a smart car, connected cars, smart health, e-health, connected house, entertainments, smart grids. So there are this is what actually the setup applications where the 5G is going to be focused. IoT is all about a lot of things, bigger than little devices. Set up end devices, gateways, messaging systems, data gathering, storage and analytics, device and data security, device management. Internet connects people and people, that is Internet of People, whereas the current context is Internet of Things, connects all things, so it is called Internet of Things. So with respect to the definition of Cisco, IoT is the networked interconnection of everyday's object with embedded computers, sensors and activators. So the expected number of devices on the internet could be 50 billion devices in the year 2020. This is estimated by Cisco. The next generation of the internet is connecting people and devices. Connecting devices results in data that open up new insight, business models and revenue streams. The insight gained from this data and in turn give rise to new services that can complement the conventional product business. The benefits of IoT are connected world will have a great impact with respect to business and social world. Private users of connected devices will see the new services enriching their relationship to the products, providing higher quality of life, comfort, security and fun. Corporate users are concerned, we have an effective system policy, cost saving and better allocation of resources. M2M versus Internet of Things. M2M focuses on connections to devices. It captures data at the endpoints and transmits it across local and wide area networks to generate specific alerts and actions. IoT includes attributes of machine-to-machine communication. However, significant additional value is created by interconnection of things, users, enterprises, and partners. The overall architecture looks like this. We have a base layer with this embedded controllers and sensor where the data acquisition takes place, and next level is networking. We have a 6LoWPAN IPv6 based adaptation layer. On top of that, routing protocol for lossy networks RPL, and then ends with the application layer with the POP and MQTT, that is constrained application protocol and message querying transport telemetry. Then ends with the cloud and analytics where the event processing, alerts, machine learning, various logical decision takes place at this application layer. We have what you call end-to-end secure and identity management was ensured. The overall layered perspective could be data collection with respect to sensor. Then we have a transport layer that is through internet, maybe in terms of mobile internet or Wi-Fi shield or Bluetooth. Then we have a application layer. We have a middleware, cloud computing, information open platform, service supporting. At the end, we have a application layer where the various environmental services, intelligent traffic, internet, intelligent agriculture, the various sectors are focused in terms of application. Sensor layer includes sensor technology, sensor based data collection, and wireless ad hoc network technology. Transport layer includes supporting and accessing technology such as private network, remote control, wireless machine-to-machine technology, mobile communication technology, internet, next generation network, and heterogeneous network integration. Application layer includes all kinds of IoT middleware such as information management, service management, user management. So the opportunities are communication sector, connected world, medical, industrial, vehicles, retail. The typical IoT network looks like this. We have a data aggregation through gateway. Then we have a tunneling node, internet. Then we have a IPv6 server. The end user could able to access from IoT server. IoT processing, sensing and embedded processing, gas, oil, smoke, temperature, network connectivity, Zigbee, NFC, Wi-Fi, cloud exploration, PTC, ThinkWorks, GE products, data analytics with respect to machine learning and artificial intelligence. IoT and fog computing, we have embedded systems and sensors, dozens of multi-service edges, core and data centers and clouds. The broad difference between cloud and fog computing are, we have a data center with the cloud, we have a edge node fog computing with the endpoints. Things connecting to things. So we have a car, get to know about the petrol status and gives you the linkage with respect to nearby petrol station or fuel stations. We have a as a result, IoT standards, high-speed scalable networks, simple, very lightweight IoT devices and cost and power constraint, developer friendly, mobile app friendly, considering scalability and performance. Long awaited dream of IoT, smart cities, smart grid, remote health monitoring, precision agriculture, industrial IoT, virtual power plants, intelligent handheld tools, changing the way of shopping in the connected supermarket. Future network could be of 3 direction, anytime, any place, any connection. How are the networks changing? Extension, more needs, more connections, IPv6, 6LoWPAN, anytime, any place, which is going to be a convergence of accessing anything. Machine to machine, expansions, broadband networks, enhancements, smart networks, data centric and connect oriented networking, context aware systems. IoT challenges, privacy, IP rights, intellectual property rights, security, data protection, cybercrime. with respect to looping opportunity in connection to Internet of Things, consumer, retail, medical, military, industrial, automotive, environmental, agriculture. VANETs, vehicle or rack networks, onboard unit, we have a roadside unit, the communication between onboard unit to onboard unit, that is called vehicle to vehicle. We have a vehicle to infrastructure, smart IoT environment, smart cities, smart energy, smart transport, smart living, smart health, smart energy, smart buildings, smart planet. IoT enabling technologies are, we have a sensor network, communication, cloud, discovery, security, future internet, knowledge aggregation, standards, nanoelectronics, embedded systems, software, system integration. Table 1 gives a comparison between these existing operating systems. Minimum RAM and ROM less than 2 KB with respect to TinyOS, 1 KB RAM, not RIoT at the order of 1.5 KB. Support, partial support, no support with respect, TinyOS works only with NSC. Full support with respect to IoT. We have partial support with respect to Contiki OS. Multi-threading support is available only in RIoT. So RIoT supports real-time capabilities. Software IoT scope. We have a IoT portal, IoT devices. The first step, fill metadata templates. Second step, update metadata. Third, keep live. Fourth, discover the services by the end user. Fifth, recursive response dispatching. Web protocols and IoT. We have a OSI layer stack, whereas IoT stack would be of 6LoWPAN, UDP, DTLS, CoAP, web objects. Now we move on to protocol stack for Internet of Things. With respect to IoT, we have a hardware, then kernel, system libraries and network stack application. Whereas with respect to network level perspective on IoT, 802.15.4 physical layer, 802.15.4 MAC. On top we have a 6LoWPAN adaptation layer, IPv6 and ICMP v6. Then we have a RPL routing protocol for low power and lossy networks, UDP, and application layer we have CoAP, constrained application protocol. What IoT demands? Low power, low cost, low memory footprint, should have provision for IPv6 with a 6LoWPAN application, separate routing protocol for low power and lossy networks, new lightweight application protocol unlike HTTP, but it should have support for HTTP also. Header compression for IPv6 against 802.15.4 MAC. Problems and challenges. Problems with end-to-end IP networking, resource-constrained IoT devices need adaptation and mapping of functions for end-to-end global IP networking. Manage a large number of devices with variety of IoT protocols. This is a problem number 1. Second problem, capability mismatch between devices. Maximum transfer unit difference simplified versus protocol stack. That is, with respect to UDP and HTTP, the header sizes are very large, whereas IoT application, the header size is supposed to be compact, where we have to use CoAP protocol. Rapid interaction between services and infrastructure, more agile communications. The variety of IoT protocols, we have a radio transmission with Wi-Fi, WiMAX, Bluetooth, NFC, LTE, MAC layer. We have first adaptation layer which solves your the particular problem what is discussed in the earlier slide, that is 6LoWPAN adaptation layer. We have a network layer with IPv6, UDP, CoAP, distributed ICE and ACE with respect to security, system layer and application layer. Setup layer levels, physical devices and controllers, connectivity. Third layer is edge computing. Fourth, data accumulation. Fifth, data abstraction. Sixth one, application. Seventh, collaboration and processes. So this is what the mapping of TCP/IP versus IoT protocol. We have a physical layer with 802.15.4, network with the 6LoWPAN, transport with UDP, CoAP with application. The overall stack layer wise: Zigbee, Bluetooth, RFID NFC, Wi-Fi, 3GPP. We have a 6LoWPAN adaptation, IPv6 and RPL, transport layer TCP and UDP, HTTP. On top of that, co-op. We have a set of applications running at the application layer. We have a link layer, that's 6LoWPAN, network layer IPv6 and RPL, routing protocol for low power and lossy networks. Application layer, we have a constrained application protocol. This sits on top of HTTP. We have a message querying telemetry transport, that is MQTT for high-end application. Now we are moving on to emulation using Contiki. So we have set up operating system. We have Contiki, TinyOS, Linux, RIoT. TinyOS, no support available on up to date, no latest support for IoT. Contiki OS so popular, RIoT upcoming and becoming popular. So the various perspective, that is in terms of RAM, ROM, C++ support, multi-threading, microcontroller unit with memory management, modularity, real time. With respect to Contiki, TinyOS, Linux, RIoT OSs are compared. The steps to install Contiki OS with Koja, that is sudo apt-get update. First we have to update your Linux kernel. The second step, the prerequisite sudo apt-get install, build essentials, MSP430, Java and MSP4 related packages have to be installed as a prerequisite. Then we have to download using GitHub, and the extracted one we have to install. That in order to extract, we have to use tar, xvf contiki.tar.gz. Then we could able to identify a folder Contiki 2.7. Inside we have a tools folder. Inside we have Koja. With using change directory, we'll have to navigate to this level. Then we have an /run command. This will give you the emulation of Koja environment. We have a protocol stack, that is sensor, connectivity and network with respect to LAN, PAN and tag wise. On top of that, we have a gateway and networking. We have a set of controllers and WAN and LAN networking perspective. On top of that, we have a management services, that is with respect to billing, reporting, device modeling, analytics, data, security, BRM. On top of that, set up end user applications, environmental, fleet management, energy, asset management, transportation, healthcare, retail, like this list goes on. Why 6LoWPAN? No method exists to make IP run over IEEE 802.15.4 network. IPv6 MTU is 1128 bytes. Not all ad hoc routing protocol may immediately suit 6LoWPAN. DSR will not fit in a packet and IODV needs more memory. Security for multi-app needs to be considered. We have a RPL. Routing protocol for low power and lossy networks. The next is co-op, that is constrained application protocol, that works on top of HTTP. Representation of RESTful web services. Setup characteristics: simple proxy and caching capability, asynchronous transport support, URI, UDP binding, reliable unicast and best effort multicast support, built-in resource discovery. So this is what the core layers of co-op. We have set up methods and transactions. So the transactions are conformable, non-conformable, acknowledgement. We have a get, post, put, delete, similar to HTTP methods. The message exchanging process, conformal, non-conformal, acknowledgement. We have a synchronous transaction, middle one is asynchronous. We have orphan transaction also supported for message exchange. Co-op steps: we have to install. After the successful compilation of the source code, we have to upload the source exe into the Sky mode. Then we'll have to configure the Sky mode using Koja. Then we'll have to set the border router then read the profile of the server, run the simulation. We could able to tap the co-op through HTTP, so we can able to measure the sensor values, and this could be controlled by writing appropriate machine learning logic at the application layer. We have a popular MQTT. This is for high-end application. We have a data analytics, lots of big data style platforms. We have a Hadoop dashboard, data storage, number of means of storing a big data. We have a MongoDB, PostgreSQL, NoSQL. We have a virtual machines, clouds, various number of hypervisor containers for scaling. We have orchestration like OpenShift for automated control and scaling. Securing IoT, this is a big question mark. We have SSL TLS. This gives partial level of network level security. Is it a problem? How many IoT devices will be in the marketplace by 2020? Gartner's expectation is 26 billion, Cisco 50 billion devices, Intel 200 billion, IDC 220 billion. So yes, every way you look at, there is going to be a problem. Important that there is a diversity in IoT platforms. Now we are moving on to specs of 5G. This is going to be a complementary to technology supports for Internet of Things. We have a 3G which supports 128 kbps when you are moving. It supports 2 Mbps when you are static. The great technology is HSPA. We have a 5G this supports data rate up to 100 Mbps. So this was developed and released in the year 2010. This supports IP end-to-end seamless connectivity in heterogeneous environments. 5G, it is next major phase of mobile. So this gives 10 times more faster than 4G. It is expected speed will be in the range of gigabits per second. It is expected to come around 2017. Lower cost than previous version. So we could see the thin sleek phone, how the 5G looks. The brief idea about 5G. Current status of 5G, that is ETSA keep working with the companies like Nokia, Ericsson, NTT Docomo, Samsung, Huawei. So these are all the setup company who drives the input to ETSA. People will be able to experience with 5G. 5G networks are likely to be rolled out commercially between 2020 and 2015. If global standards are finalized by 2019, the earliest commercial deployments could happen in 2020. 3G and 4G answer does run on the 5G networks. The answer is no. 5G requires new chipset and devices capable of supporting speeds upward of 10 gigabits per second. 4G and 3G run at fractions of that speed. The great comparison was given. 5G, the deployment in the year 2020, the data rate in the order of 1 gigabits per second. The technology could be a 4G plus quad W, that means wireless World Wide Web. Whereas 4G supports, we have a IP seamless multiplexing, could be CDMA. Core network is internet. We have service, that is dynamic information access, variable devices with artificial intelligence capabilities. The 5G layers could be open wireless, which is data and physical layer are going to be open. Network layer is split into two sectors. One is lower network and other one is upper network. Session and transportation put together open transport protocol application. The data transfer architecture with respect to radio access network, GSM, GPRS, Edge, UMTS, LTE, WiMAX, Wi-Fi, CDMA 2000, evolved data optimized core, CDMA 1, IS95, ISP. These are all the various radio access network. We have aggregator, we have a global IP platform, IP and IP. The nano core uses AP nanotechnology, cloud computing. The other end, the global market is going to be search engine, defense, astronomy, transportation, communication, medical, education, government, private portal, public portal, banking. The 5G applications are wearable devices with artificial intelligence capabilities, 5G iPhones with sixth sense technology, global networks, voice over IP enabled devices, radio resource management, media independent and over. So 5G spectrum could be a millimeter wave communication. This supports virtual link MIMO and with device to device connectivity. We have a avalanche traffic volume that is keep increasing in the order of 1000 times. The massive growth in the connected devices, large diversity of use case and requirements. We have a METAS like ETSI. We have a mobile and wireless communication enablers for 2020 information society, that is METAS. The volume of the data could be 1000 times greater than current level. The number of devices could be 50 in the order of 50 to 500 billion. The data rate support in the up to 10 gigabits per second. The latency is going to be end-to-end with a minimum millisecond. The battery life could be 10 times longer longevity. The future 5G could be the integration of the existing 3G, 4G and Wi-Fi. So we'll have a evolution complementary to each other. So the data rate in the order of 1 to 10 Gbps, capacity 36 terabits per month per user, that is 500 GB minimum. Spectrum, high frequencies and flexibility, energy 10% of today's consumption, latency reduction 1 millisecond, tactile internet, device to device connectivity, resilience, reliability 99% within time budget, coverage greater than 20 dB for LTE, battery that is 10 years, device per area that is to be 300 per access nodes. So with respect to ultra dense network, these are the parameters are focused. Ultra reliable network, these are the parameters. At the end, massive machines focus on the last three. What will 5G look and feel like? Use millimeter wave, massive MIMO, native support of IoT and M2M, Wi-Fi first network, virtualized network functions and software defined networking, device to device, vehicle to everything, privacy by design. Spectrum sharing and splicing, seamless networking with licensed and unlicensed spectrum bands, service creation time reduced by 99%. Some of the performance goals of 5G under discussion are average data rate 300 to 500 Mbps, less than 1 millisecond latency, 1000 times reduction in the power, very high reliability including indoors, deep indoor coverage with the order of 20 dB, 30 times higher device density, 10 to 100 times connected devices, 100 times greater than the average data rate, significant higher security requirements. Thank you for your attention.